All right, well, having given out all the answers to the test, we are now able to start recording. Right, absolute stereochemical configuration. So beginning with a stereocenter, you're going to first remember that there's 4 things attached to the stereocenter, and they're different, and we need to assign them each a priority score from 1 to 4. So it's usually easiest, and it's going to be same rules as with E and Z, so it's by weight of the atom by atom comparison. If I compare all of these atoms, carbon, carbon, carbon versus hydrogen, hydrogen is the smallest, and so this is going to have priority 4. Then I have to compare the other 3 groups. They're all carbons, so we do our tiebreaker procedure, which is we write what they are bonded to in order from heaviest to lightest. The methyl group here is bonded to 1 other carbon and 3 other hydrogens. The carbon here is bonded to 2 carbons and 2 hydrogens. This carbon is bonded to an oxygen, to 2 carbons, and to a hydrogen. So in the first round of the tiebreaker, oxygen wins. So this is priority group 1. Then if we compare the other 2 groups, it's a tie. So we go to the next one, which is carbon versus hydrogen. Carbon wins. This is priority 3. Oh, right, thank you. Can't count today. This is priority 2, and this is priority 3. You with me so far in assigning the groups? Now, we draw an arrow from 1 to 2, from 2 to 3, and from 3 back to 1. And we note that that is clockwise rotation, or CW. And we also notice that the lowest priority group, proton, is down away from us. And if those 2, the lowest priority group is down away from us and we see clockwise rotation, then we conclude that the stereocenter is R. That's R, that's from the Latin for right-handed, rectus. And so R we will use for clockwise rotation when proton is down. Why do I specify as proton is down? Well, you can go back and make a model of this compound, flip it over, and if proton is coming out towards you, rotating from priority group 1 to 2 to 3 and back will actually be counterclockwise. Yeah?
And we just know that proton came down
because of the dash. Yeah, we know that the proton's going down away from us because of the dash here. And the wedge says the methyl group's coming out toward us.
Okay. But what I mean is, because that wouldn't always be drawn, so we know to draw it down because the methyl group.
Right. Oh, if the proton isn't drawn, you know it's there because, and it's going down because, yes, the methyl group is coming out. So when you're assigning stereocenters, it may be a good idea to draw the protons that are implied but not shown. Okay? All right. For the other stereocenter, and we'll choose, just for sake of not having to redraw on the same molecule, we'll look at the second stereocenter here. Again, we will compare the atoms that are the 4 atoms that are bonded to the stereocenter. We have oxygen, 2 carbons, and a hydrogen. Oxygen is clearly priority group 1, and hydrogen is clearly priority group 4. But between the 2 carbons, we'll have to do the tie-breaking procedure. Up top, you have a carbon that's bonded to 3 other carbons and 1 hydrogen. Here you have a carbon that's bonded to 2 other carbons and 2 hydrogens. So it's clear that here is priority group 2, here is priority group 3. Draw the arrow from 1 to 2, 2 to 3, and 3 back to 1. That is counterclockwise. And again, the lowest priority group, proton, is down. Therefore, that stereocenter is S. And that comes from the Latin sinistre, which means left. and left-handed friends out there, I think you should be offended by that because the term sinister originally meant left-handed. It has come to mean like evil and nefarious. So you don't take it personally, and I'm sorry that it ended up that way. Adam is left-handed, and he's not evil most of the time. Adam's my son, by the way. Sorry. Let's see. Questions about how to assign stereochemical configuration? Yes?
So if it's clockwise, but H is up, would it be switched?
Yep. If it's clockwise but H is up, we switch it. So let's do this example. We already assigned priorities over on the left, so I'm not going to repeat that process. Proton is 4. This carbon is 1, the methyl group is 3. 1 to 2, 2 to 3, 3 back to 1. It is clockwise, but proton is up. If proton were down, we would have said R, but because proton is up, we switch and it's S. The alternative is to redraw the molecule in from a direction where proton is down and make the assignment, and you can. I just have found that plenty of people make errors when redrawing the molecule, that if you can keep it the same way but remember the switch, maybe you're less likely to make mistakes. We can go ahead. Yeah.
That one. What if the carbon that is labeled 3, wouldn't that be 2 because it's bonded to 3 carbons, whereas the 2 is bonded to 2 carbons?
Carbon here that's labeled 3.
Sorry, no, the one that is 1, 2, 3 carbons and hydrogen. The yellow one.
The yellow one, yeah, that is the stereo center we're assigning. So we don't count that in the priority. We're looking at the 4 things that are attached to that carbon. Yep. Anybody else? Yeah.
If the lowest priority group is something besides hydrogen, do you still flip it?
If the lowest priority group is something besides hydrogen, do you assign it exactly the same way? Should we make up one like that? All right, we'll keep the same situation, only we will add a methyl group there. So let's assign this stereo center. I'm not sure what configuration it is, so we'll start there. Let's see. So it becomes a little bit trickier to identify the lowest priority group because 3 of the 4 things attached to this carbon are all carbon. So I start by just oxygen versus carbon. Oxygen is the highest priority group. And then I move on immediately to my tie-breaking procedure. Oops, but I don't do that because that was skipping the atom. I'm looking at the atoms that are bonded to the stereo center. They are all carbons, so nobody wins at that stage. I enumerate what they're bonded to. Here I have something that's bonded to 3 carbons and 1 hydrogen. Over here I have something that's bonded to 2 carbons and 2 hydrogens, and then here I have something that's bonded to 1 carbon and 3 hydrogens. So I start going down the list atom by atom. It's a tie there, but then I go here and this group loses, so that's priority 3. And then here the group on top wins, that's, sorry. We've already assigned 1, so we're trying to decide who's 2, who's 3, and who's 4, right? So carbon, 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 that's a tie. Carbon, carbon, hydrogen, that guy's the loser, so that's 4. Carbon versus hydrogen, this is the winner, so this group is 3 down the bottom, and this group is 2. So you have 1, 2, 3, and 4 for the methyl group.
How would that rotate?
So I just ignore the 4 for now. I draw the arrow from 1 to 2, from 2 to 3, and from 3 back to 1. I note that that is clockwise rotation, and I note that priority 4, that's not how you spell priority, is it? Priority, whatever, 4 is up. So, yes, you know, guys, I'm really sorry about that. Half the time I get right and left wrong, exactly. Well, there's no other way to get it wrong, but yeah, most of the time my first attempt at right versus left is incorrect. It's genetic, I think. My grandma says she used to have to tell my grandpa, "Your right hand, Dale. Throw a rock. Throw a rock." Okay, yeah, that's my right hand. Right, counterclockwise, but priority group 4 is up. So if priority group 4 was down, counterclockwise would be S, but since it's up, it's R. So that's how we do it. The worst possible situation is where somebody draws the priority group 4 for you in the plane of the page, and then you have to just adjust your drawing. All right, so that's assigning stereocenters. Practice that. The nomenclature for that, the rules are the same as they are for E and Z. You would put these numbers in parentheses. You would put these letters in parentheses at the beginning of a name with the number of the stereocenter indicated where you have more than one stereocenter. All right, so I want to talk now about why. So practice that. Assigning R versus S is just like E and Z. It's easy for me to give you several questions on the exam about it, and frankly, as you probably found with E and Z, when you got a 50-50 shot, it's possible to get the right answer many times in succession for the wrong reason. So you got to try enough problems so you know you're getting it right for the right reason. Okay, so stereochemistry plays an important role in biology and actually in making decisions related to healthcare. So shown here are 2 enantiomers of a molecule called Ameprazole. This is a proton pump inhibitor that is prescribed to prevent acid reflux and help with ulcers and so on. The stereocenter, you can just take for granted that it's a stereocenter. This is a sulfur that's attached to 4 different things in the sense that it has a lone pair that stays in the same place. I think I mentioned last time that nitrogens attached to 3 different things and a lone pair are not stereocenters because they can invert rapidly. Sulfur doesn't, I think because of its size. But I would not ask you to assign these stereocenters. You can just accept, hopefully on my word, that they are in fact enantiomers of each other. And it's easy to produce a one-to-one mixture of enantiomers. In chemistry, as we will see, you don't get chirality from nowhere. And if you have a reaction where the reagents are not chiral and the starting material is not chiral, but you make a stereocenter, you must get both configurations. And we'll see some examples of that very soon. So it's easy to produce a one-to-one mixture of enantiomers. We call that a racemate or a racemic mixture for historical reasons. But you can go to Target, and I don't know what I was thinking in terms of 100 milligrams. That's actually probably too much. At Target, the dosage is 20 milligrams. This is available over the counter. It used to be sold, and still is, under the brand name Prilosec. And I believe it was it AstraZeneca or was it GlaxoSmith? I can't remember, but the drug company that made this sold a lot as a way to help people with acid reflux. And they used the one-to-one mixture of enantiomers, even though they knew that only one of them was the active compound. So, as you may know, biology is chiral. You are made of amino acids and nucleic acids that have stereocenters. The proteins that do all the work inside you are chiral. And chiral molecules can distinguish other chiral molecules in the same way that your right hand can distinguish between somebody else's right hand and their left hand, right? You go in for a firm handshake, right hand on right, or perhaps left on left, and that's normal. If you go in for a firm handshake with right hand and somebody gives you their left hand, it ends up feeling uncomfortable. And has a different outcome, right, with your job interview probably. So biology can distinguish between, one chiral molecule can distinguish between two enantiomers. But in this case, they knew through safety and efficacy studies that the other enantiomer wasn't a problem. And so they sold this one-to-one mixture, and it was easy to manufacture. Well, in the United States at least, patents have a lifetime. When you patent a drug, you have a limited number of years where you can exclusively market that drug and try to recoup your costs. And I think it's something like either 14 or 17 years from filing the patent. And usually it's several years after filing the patent that the drug finally gets through clinical trials. So drug companies have a limited window to recoup their research and development costs. And so the end of a patent is sometimes called the patent cliff. The end of a patent lifetime when other companies then can make the molecule and market it is a time where revenue drops off for a drug company. So it's this really sort of horrible fiscal cliff that they go off of. In the early 2000s, the company Pfizer, the patent on Lipitor or atorvastatin expired, and they were making billions of dollars on that every year, and then suddenly it was available much cheaper, and their revenue stream started to dry up on that particular thing. So drug companies always have to be thinking, what's the next thing we're going to do? When they have a good drug that they have previously marketed as a one-to-one mixture of enantiomers, what sometimes they will try to do is then patent the active enantiomer, get a fresh patent on the active enantiomer, and sell that. And that's a new preparation, a new molecule, and they can extend the patent lifetime. And this was the case for Prilosec, the company that made it, and I wish I remembered what it was, we can look it up, did something that in the drug industry is called the chiral switch. They came up with the pure S enantiomer of omeprazole, which, if you look at the generic name for omeprazole today, or for this molecule today, it's esomeprazole, and that's literally spelled out the S in stereochemical configuration. And they sold this as, oh, I need to move the box, right? Sorry. And suppose somebody told you, hey, you want to prescribe, you're a physician, and somebody says, you want to prescribe esomeprazole because 10 milligrams of esomeprazole is more effective than, is at least as effective as 20 milligrams of regular omeprazole. Should you be impressed by that statement? Why not? It's the same dose of the active molecule, right? Nevertheless, I can remember growing up and watching TV, and they were pushing Nexium, the purple pill, really hard. And the reason they were doing that is because they didn't want to lose money to all the generic drug manufacturers who were merrily making the one-to-one mixture of enantiomers while they were trying to market the pure enantiomer. Now, the story is that I was at Target the other day getting some of this because Adam, my son Adam, likely has some kind of condition with an inflamed esophagus that's related to acid reflux, and so this is one of the things they prescribed for him. Interestingly, you can get the pure enantiomer for a couple dollars less than the racemic mixture, which I don't really get or understand, but in either case, you can take either one and it's fine. They followed up with some studies, and it seems like if you take the pure enantiomer in the body, it actually gets racemized into both enantiomers anyway. But there may be some benefit for people that have a certain cytochrome P450 enzyme that helps metabolize the drug. So, but it's only a marginal benefit. And as I said, they knew previously that there were no safety issues associated with either enantiomer. Yeah, go ahead.
Assigning RMC to this molecule, you count the lone pairs as.
Yeah, if you were going to assign, I wouldn't ask you to do this, but if you were going to assign R versus S, yes, the lone pair is the low priority group. So, 1, 2, 3, S. Yeah.
So I'm sure you explained it, but I just completely lost it. So how is the 10 milligrams the same effectiveness as the 20 milligrams when the same molecules you share in both?
Right. So a 20 milligram mixture would have 10 milligrams of the two enantiomers, would have 10 of the active enantiomer and 10 of the inactive enantiomer.
So is the inactive enantiomer just kind of
dead weight?
Oh, okay.
Yeah. Now, there are some drugs for which the inactive enantiomer is not safe, is not dead weight. So the classic example of that is the drug thalidomide, which was an antiemetic prescribed to help with morning sickness during pregnancy. And the enantiomer A was the effective antiemetic and preventing throw-upping, whatever. But under biological conditions, it was easy to remove this proton, and you'll learn why in 352, and then you could reprotonate the conjugate base from either side, and you would generate some of the other enantiomer, which is not innocuous, it's a teratogen. And people were taking this at exactly the time during pregnancy where teratogens could have a terrible effect. And so that's a very horrible and scary story. This is a case where it wouldn't have been good enough to just use the one enantiomer, because in vivo it's going to get turned into both of them anyway. And so this is a part of safety and efficacy studies, and the FDA is very, very careful with that kind of thing. So you may wonder why different enantiomers can have different biological effects. The reason, as I said, is that diastereomers have different chemical and physical properties. And you can expand your definition of diastereomers to include non-covalent complexes. So our right-hand handshake versus right-hand left handshake, those are two diastereomer situations, right? The right handshake is the enantiomer of the left handshake, but the right-left handshake is a diastereomer of the right. Yes, we're trying it. It was weird, right? Yeah. The right-left handshake is the diastereomer of the right handshake, even though we haven't made any covalent bonds. So I'm showing you here an image from a crystal structure of a protein with a drug molecule bound. And I didn't write down what the protein was or what the drug molecule was. So sorry about that. But here is in orange one of the enantiomers. And it's in the active site. It is an inhibitor of this particular enzyme. And it is forming non-covalent interactions with various groups on the enzyme. Here is that guanidinium side chain that you saw on the exam. Here is an amide group hydrogen bonding with a carboxylate. Here's a water molecule hydrogen bonding with an amine. Here's a carboxylate group hydrogen bonding with an amine. Anyway, it fits in that active site and interacts with the right groups. There's a stereo center here that I have highlighted, and you can't see all the three things. It's bonded to this nitrogen, this carbon, and that carbon. And then there's a proton sort of jutting out in this direction. Now, they've also crystallized the complex of the other enantiomer with this same protein. Notice that the other enantiomer is the mirror image of this, but the protein is not the mirror image of what it used to be. Now all the functional groups on the drug are on totally the wrong side to interact with the protein. And if you don't bind with the same affinity to the protein, you don't have the same biological consequences. So these two situations are diastereomers of each other, and they have different properties, different outcomes. And then here's the merged image, so you can see they actually do occupy completely different spaces. You can even see that the protein in some cases rearranges some of its side chains to accommodate the presence of this other enantiomer. And those kinds of changes in shape can have far-reaching consequences in biological activity. Yeah.
There's a question
Excuse
like
me.
this on the exam.
Yeah, where you
Oh, shoot. Say what? Go ahead. Okay, right. So let me see if I understand the question. Will you be required to draw this on the exam? Yes, take a picture of it now in your brains, because no, you're not going to be drawing it, right? Would I require you to assign stereochemistry there? If I did so, I would have to tell you what all the colors mean. So blue is nitrogen, orange is carbon, but it would be unlikely for me to give you that and say assign. You are probably not used to this kind of drawing. I am, because I've spent years looking at crystal structures in a program called PyMol. This is just a way of representing biological molecules. You may learn about it more in 352. You don't need to memorize anything here. The point is simply that the two diastereomers fit into the same protein differently. Yeah?
I had a question. This is kind of going back. If you scroll up to, you showed that was like an S configuration.
Yeah.
So the one right below it, is it also S, or is it?
This one would be R, because above, and this is why I wouldn't ask you this question, the fact that this group is up tells you that the lone pair is down.
Oh, so okay.
And the fact that this group is down tells you that the lone pair is up. Yeah. Yeah, and we're not going to assign those kinds of stereo centers, but they do exist. Yeah.
Just a quick question about pictures below.
Yeah.
So the two, like the hex, that's a protein. What was that?
So, okay. Here is the small molecule inhibitor, and everything else that's in gray, those are amino acid side chains within a protein or enzyme that does something.
Okay, so the two inhibitors are enantiomers of each other.
Right.
But the enantiomers plus the protein stuff make diastereomers.
Exactly. The orange and purple are enantiomers of each other, but when bound to the same chiral protein, those two complexes are diastereomers. Yep. Right. The chiral protein can tell the difference between the two enantiomers, in the same way that your right hand can discern between someone else's right and left hand. Right? Also, I mean, this is kind of fun. I mean, already you know it, but humans are also not superimposable with their mirror images. So at some point, children realize that who they see in the mirror is not the same thing as everybody else sees. So when you look at the mirror, you're looking at your own enantiomer, which is not the same as you. But anyway, weird. Okay. I'm debating what to do here, because there is a way you can distinguish between enantiomers. It involves something called optical rotation. It's important if you were going to be chemists. It might show up on the MCAT or the DAT, but it's not that important otherwise. So yeah, maybe I won't spend a huge amount of time on this because it involves a little bit of physics that I don't understand. So you're going to have to suspend disbelief for a little bit. What have I attempted to draw here? Well, it doesn't matter. I'm going to erase it. All right. You ever had polarized sunglasses? Polarized lenses, right? This involves a material that filters out all the photons that are not oscillating in the same direction. And I don't understand the material science about how that happens. Nevertheless, if you have a polarizing lens or a polarizing filter, and let's say the axis of polarization is here, then before, light's going to pass through, and I'm going to try to represent the ways in which the various photons are oscillating. One of them might be oscillating in this direction, another might be oscillating perpendicular, there might be other oscillations all around. But once we go through the polarizing filter, all of the photons are oscillating parallel to the filter. I think I'm just talking about the electric component of the electromagnetic field oscillation, but whatever. Okay, so that's principle one. A polarizing filter makes it so all the photons oscillate in the right direction. Principle two is a little bit weird, and if we were in my grad level OChem class, we would talk about this in more detail. You can think of polarized light as a one-to-one mixture of polarized light that is rotating in the clockwise direction and polarized light that is rotating in the counterclockwise direction. Just think of it this way. If they're rotating if you have these two vectors rotating opposite each other, the sum of those two vectors is going to be a single vector oscillating up and down because the x components cancel each other out. I'm sorry, that makes no sense to you. It may not. It makes precious little sense to me. But the idea is that light itself has a right-handed component and a left-handed component. And because of that, a chiral molecule will interact with right-handed light different than left-handed light. And the physics of that aren't important, but what happens is if you pass this light through a cylinder filled with a chiral sample, the chiral sample will absorb one-handedness of light more than another. And on the other end, what that looks like is the plane of polarization rotates. So whereas before the chiral sample, all the light was oscillating parallel to the axis of polarization here, now it's rotated through some angle. And that process is called optical rotation. So if you take, how this is done isn't that important, but if you take the initial plane of oscillation and then the new plane of oscillation, you measure the angle between the two of them, that's optical rotation. Okay, and we call that angle, instead of calling it theta, we call it alpha, and we normalize it for path length and sample concentration, and we give it that, put it in brackets. So two enantiomers will rotate light by the exact same amount, but in opposite directions, because the physical basis for this is that the enantiomer interacts with one-handedness of light different than the other-handedness of light. So as an example, I'm going to draw a chiral molecule here. Its precise identity and structure is not important. I'm just drawing it for you so that you can see the stereocenter and so that the data I can show you are not made up but are real. Here's the stereocenter. Oh, and here's another one. And by this point, you're really glad I'm not making you know this structure. But wait, there's more. Anyway, the optical rotation of this enantiomer, this molecule is called quinine, it's a natural product, is 165 degrees in the positive direction. In contrast, its enantiomer, I don't know what its enantiomer is called, so I'm going to call it enantioquinine, rotates plane polarized light by 165 degrees in the opposite direction. If you had a mixture of 50% quinine and 50% enantioquinine, the ability to rotate light is additive. So the 50% of your mixture will rotate light by 50% of this amount, and the other 50% of your mixture that's the enantiomer will rotate light by 50% of that amount, and the overall rotation of that 1-to-1 mixture is 0. And we call that mixture optically inactive because it doesn't rotate light anymore. And the reason it doesn't is we have an identical mixture of two enantiomers together. The one rotates this direction, the other rotates in that direction. They cancel each other out. There's no overall net rotation. Now, you can use the optical rotation of a mixture to determine its composition. So suppose I have a mixture of unknown composition of, we'll call quinine Q, and we'll call enantioquinine Q with the star. And I observe, so I have a mix that is X% Q and Y% Q star, where X plus Y equals 100. And I observe for the mixture, I observe an optical rotation of 82.5%. But I know, and it's in the positive direction. And I know that the expected optical rotation for the pure major enantiomer of my mixture is plus 165. So right away, just because of the sign of the optical rotation, I know that Q is the major enantiomer and that its Q star is the minor one. If it weren't that way, if they were just 50-50, I would get 0 rotation. So the fact that I'm getting plus 82.5 rotation tells me I have more of quinine than I do of its enantiomer. And it's actually quantitative. So if I take the observed optical rotation and I divide it by the expected optical rotation for the pure major enantiomer, that number happens to be 50%. That's not the composition of the mixture. That's what we call enantiomeric excess. That means how much more of the major enantiomer do we have than the minor one. Okay, so how much more of the major enantiomer do we have than the minor one? That's, we've already decided that quinine is the major enantiomer. So we know that X% minus Y% has to equal 50%. And we also know that X plus Y has to add up to 100%. So at this point, 2 equations, 2 unknowns, or you can just say, okay, what numbers add up to 100 but their difference is 50? Yeah, go ahead.
Just to make sure I'm on the same page. An optical rotation of 0 means that the substance is opaque.
The optical rotation of 0 doesn't mean the substance is opaque. It just means it doesn't rotate plane polarized light, and therefore it either is not chiral or it has a 1-to-1 mixture of enantiomers. Because remember, optical rotation is kind of like absorbance. It's kind of a Beer's law issue. It's additive, so if 50% rotates the mixture this way and 50 rotates it the other way, those 2 rotations will actually cancel each other out. So when we have a rotation that we observe and it's different from the expected, we can divide what we observe by what we expect. We get 50% enantiomeric excess, which would tell us that we actually have 75% quinine and 25% of its enantiomer. Okay, so again, there's a lot of stuff you could do with that, but that's the level at which we'll look at it. Make sure you're able to solve a problem like that. There should be some examples in your text that will give you some practice. Say what?
Is it without some problem?
Be able to solve a problem like that. Yep. All right, see you Wednesday.